So in this lecture I will discuss pointwise differentiation of measures. So the main theorem will state the following. Consider function f, which is monotone increasing. We want to show that f can be decomposed as the sum of three functions, f1, f2, f3, where f1, and I will be precise later on, is a function which I will call a jump function. So typically it's a function which looks like that, so it increases only by jumps. But I will be more precise later on. I just want to now state informally the main result. f2 will be absolutely continuous. And this, we have seen in the previous lecture what are the absolutely continuous functions. And f3 is what we'll call a singular function. And by a singular function, I mean a function which is continuous and whose derivative is equal to 0 almost everywhere. And we have seen an example of a singular function in the previous lecture when I presented the Cantor function. So this is the main result, and we will do that in several steps. I will start discussing a bit what are the jump functions and their connections to the measures on the line. So let me represent by M the measures on the line with the Borel sigma algebra, such that I will ask them to be sigma finite, and also that the measure of the segment minus infinity to x or minus infinity to 0 to be finite. This second assumption is not needed, but I will assume that because it helps me with the notation. So I will explain in a second why I'm assuming that assumption, and I will show that, well, it's not, this assumption is not needed, it just simplifies notation, and but we will always assume that these functions are sigma finite. So now, given a measure mu in M, I want to associate to this measure an increasing, monotone increasing function, which I will represent by f of mu. So f of mu will be a function from R to R plus actually, and I'll define f mu of x to be the measure of the interval minus infinity to x. Okay. And well, since I'm assuming that mu minus infinity is 0, it's finite, you see that mu minus infinity x, it's always finite. Well, if x is smaller than 0, then this expression is bounded by that one, which is finite. If x is larger, well, this measure, it's bounded by mu minus infinity 0 plus mu 0x. This expression is finite because I'm assuming mu to be sigma finite. That one is finite by assumption. Okay? And you see that, well, it is this assumption which allowed me to define f mu in this simple way. If I didn't have this assumption, okay, I can still define a function. And how would I define? Well, I'll say I want f mu of minus infinity x to represent f mu x, to represent mu of minus infinity x. Okay. Well, but this is plus infinity, so what I will do is the following. I will set f mu of 0 to be equal to 0. Okay, so this is a normalizing factor, and then if x is positive, well, I want f mu of x to be given by this expression. X is positive, I can write this expression as m minus infinity 0 plus m 0x, right? Well, that would represent f mu of 0, but I set f mu of 0 to be 0, so this expression is 0, and therefore I will define f mu of x to be mu 0x for x positive. And if x is negative, well, again, I want f of mu to represent this expression, but I can represent this expression, I will add 0, x 0, so I will write that as minus infinity 0 minus mu x 0. Right? Because, well, I have here a formal identity. It's not an, well, it's an identity, but this expression is equal to plus infinity and that one also. But since I assumed, I'm supposing that this should represent f mu of 0 and f mu of 0 is 0, so I'll set f mu of x to be minus m x 0. Okay? So without this assumption, I still can define a function f in this way. It will be 0 at 0. It will be given by this identity if x is positive. If x is negative, it will be given by that one. And everything I will prove and say for this function will hold for this function without this assumption. But to avoid having two different expressions for the function, I will assume that mu of minus infinity of the interval minus infinity 0 is finite in order to be able to define this expression, so to have f given by only one formula in terms of mu. So again, let me insist that this assumption is not needed, but it will simplify the notation, and well, we don't lose too much of generality by assuming this expression. So from now on, and from the entire lecture, I will assume this condition, and I will define f of mu by this formula. And I claim that, well, f mu at minus infinity, and by that I represent the limit as x tends to minus infinity of f mu of x, that this is equal to 0, that f mu of plus infinity it's equal to mu of r. So you see f at minus infinity will be 0. Then I claim that f mu it's monotone increasing. And finally, that f of mu is right continuous. Okay. So let me prove these three properties, and they are all very, very easy. So let's prove that f mu of minus infinity is 0, but f mu, this by definition is the limit as x tends to minus infinity of f mu of x. And this limit, it's the limit as x tends to minus infinity. F mu of x by definition, it's minus infinity x. Well, and this set is decreasing to the empty set. So by the continuity from the above of the measure mu, this is equal to mu of the empty set, but mu of the empty set is 0. And this proves that f mu at minus infinity is 0. And in the same way, if I take x converging to plus infinity, so I have here instead of minus infinity plus infinity, so now x it's increasing to plus infinity, and again, well, this set it's increasing to r, and therefore by the continuity from below, this measure, well, this number it's converging to the measure of r, which is what I wrote here. So the first property, it's very easy to check. Let's prove the second one. Well, the second one, it's also very simple. Take x less or equal than y. So f mu of x, it's minus mu of minus infinity x. Since x is less than y, this set is contained in the set minus infinity y, and therefore the measure of this set is less than the measure of that set, and this is f mu of y. Okay, so f, it's a monotone increasing. That's also very easy. And finally, let's prove the third property, that f of mu is right continuous. So let me take y decreasing to x. F mu of y, it's mu of minus infinity y. So if y is decreasing to x, this set, it's decreasing to minus infinity x. And again, by the continuity from above of the measure mu, the limit as y decreases to x, which is the limit as y decreases to x, it's equal to mu of minus infinity x. And this is f mu of x, which proves the right continuity. So let me just see what happens if you take the limit as y increases to x. So let me take the limit as y is increasing to x of f mu of y. This is the limit as y increases to x of f of mu minus infinity y. And as y increases to x, this set, it's increasing, well, to the set in which it's open, it's the interval minus infinity x with open at x. So this is mu of minus infinity x, and so this is not f mu of x, but it's mu of minus infinity x minus mu of x. Okay, minus mu of x. So I can write this minus infinity x as the closed interval minus the point, and therefore this is f mu of x minus mu of x. Let me represent this expression as, well, this is the left limit at x of f mu. So let me represent that by f mu of x minus. So the limit of f mu to the limit in the left direction. And what we see is that, well, f of mu will have a jump at x if and only if mu of x is positive. So what we just showed is that f mu of x minus its limit, f mu at x minus, that this is equal to the measure of the point x. Which means that if this measure, the measure of the point x, it's equal to 0, then the left limit, it's equal to the right limit, because the right limit it's f mu of x, because f mu it's right continuous. So if mu of x is equal to 0, the function, the right limit, it's equal to the left limit, which means that f is continuous. While if it's strictly positive, this means that f mu has a jump at the point x, and the jump, so there is a limit, it's right continuous, and this jump is exactly equal to mu of x, right? So these are the three properties of the function. So once you have a measure mu in this set M, you can define a function f mu by this formula, and we proved 4 properties of this function: that the limit at minus infinity and plus infinity are given by this expression, that it's monotone, it's right continuous, and that the jump is given by the measure of the point. So let me call f the set of functions f from R to R plus, such that f at minus infinity it's equal to 0, f it's monotone increasing, and f it's right continuous. So we've seen that if I have a measure mu, I can obtain a function by defining f mu of x as mu of minus infinity x. Now I claim that we can go in the other way around. If we take a function f in this family f, then we can define a measure, and I will represent this measure by mu of f. And the measure, let me define this measure. So remember that we have a semi-algebra, and the semi-algebra is composed by the following sets. The sets minus infinity b, ab, a plus infinity, r, and the empty set. Okay? So this forms a semi-algebra. So let me define this, the measure of such a set. So mu f of a set minus infinity b will be given by f of b. Okay? Mu f of minus infinity of ab will be defined as fb minus fa. Mu f of a plus infinity will be defined by f of plus infinity, which is the limit of fx as x increases to plus infinity, minus f of a. And this can be plus infinity if the measure, if f at plus infinity is equal to plus infinity, which means that the measure of this interval will be equal to plus infinity. Mu f of r will be f of plus infinity, and finally mu f of the empty set will be defined as 0. Okay? So this defines a function mu f on this semi-algebra, and what I claim is that you can prove that mu f is sigma additive on S or on the algebra generated by S, in the same way as you proved that the Lebesgue measure is sigma additive on S or on the algebra generated by S. And therefore, by Carré-Theodori theorem, you can extend this measure mu f to the Borel sets of the line. And so, once you have a function f belonging to this family, you can define the measure associated to that function through this formula. And you will need the property of the right continuity of your function, well, to be coherent here, to show that, let's say that f, for instance, it's continuous from above. So you'll need these assumptions in order to have, well, this one will guarantee that your function, that your measure, it's non-negative, so that the measure of an interval, it's non-negative. That one, as I said, and this one, well, simply will tell you that you are indeed in this set, that mu of minus infinity 0 will be finite, or mu minus infinity x will be finite. So we've seen that we can, given a measure mu on M, we can define a function f on f, and now with these formulas and the Carré-Theodori theorem, we can go in the other way. So given a function f with these three properties, by these formulas, we can construct a measure in the Borel sigma algebra of the line, for which this relation holds, right? Because you see here, this is exactly the relation which is written over there. So there is a one-to-one correspondence between these two sets, and we will play with this correspondence in order to prove the theorem I stated at the beginning of this lecture. So let me talk about atoms. So let's fix a measure mu in my set M, and I will say that a point X in R is an atom for mu if mu of X is positive, strictly positive. Okay. And what I claim is the following. Well, let me represent by D the set of all atoms, maybe D of mu, the set of all points X in R, which are atoms for mu, so the points for which mu of X is really positive. And what I claim is that d mu is countable. Okay. Well, why is that so? I can, of course, let me call d n mu. Instead of taking all points in R, I will take all points in the interval minus nn, such that mu of X is positive. And it's clear that d mu is equal to the union of d n mu. So in order to prove that d mu is countable, it's enough to prove that d n mu is countable. So what I need to prove is that d n mu is countable. But now let me call d n k mu the set of points X in minus n such that mu of X is larger than 1 over k. And again, it's clear that dn of mu is equal to the union for k larger than 1 of d and k mu. Okay. It's clear that d and k mu is contained in d and mu, right? If mu x is larger than 1 over k, then x of course belongs to this set. And on the other hand, if mu of x is really positive, well, it will be larger or equal than 1 over k for some k. So these two sets are equal. Therefore, in order to prove that the set d and mu is countable, it's enough to prove that the set d and k mu is countable. Well, but I know that mu of d n k mu, this set d n k mu, it's contained in the set minus nn. Okay, so this is smaller than mu n n, because this set, it's of course contained in the set minus nn. On the other hand, well, the measure of this set, it's larger than, let me represent by dn k mu the total number of points of this set. And let's assume that this set has more than m elements. Okay. Now I claim that, and let me call, so x1, xm. So I'm assuming that the total number of elements of this set is larger than m, so I can find at least m elements. Let me call x1 up to xm the elements of this set. This means that mu of d n k, mu, it's larger or equal than mu of this set x1, xm. Okay, because, well, these points x1, xm belongs to this set, so this set is contained in that one, therefore the measure of this set is contained. The measure of this set, it's just the sum of these measures. But since each of these points belongs to that one, to that measure, they have all a measure which is at least 1 over k. So the measure of this set is at least m divided by k. Okay? There are m points, and each point has mass at least equal to 1 over k, so the measure of that set is equal to. So what do we have? What have we proved? That m divided by k, it's less than this expression, which is less than that one, and therefore we conclude from these inequalities that m divided by k, it's less or equal than mu of minus n, and therefore that m has to be less or equal than k times mu of minus n. Well, this is finite because mu is sigma finite, so this is a finite number. K, it's fixed because I want to prove that this set it's countable, and what this proves is that the total number of elements of this set, m, has to be smaller than k times mu n. So the total number of this set is actually not countable but finite, because the total number of points of this set has to be bounded by k times mu, the measure of the interval minus n. Right? So this proves that these sets are finite, and therefore that this set is countable, which is what we wanted to prove. So this shows that the sets of atoms of a measure which is sigma finite, it's countable. So this leads me to a definition. I'll say that the measure mu in M is discrete if there exists a set D such that, and which is countable, and since it's countable, let's write D as xj for j larger or equal than 1. It can be finite. If there exists a set D which is countable and weights pj, such that the measure mu of a set A, so A it's a Borel set, well, will be given, I'm summing over all j's such that xj belongs to A, and I'm summing the weights pj. So another way in, so this is what I call the discrete measure. The measure is discrete if there exists a countable set and a countable number of weights such that the measure of any set A can be expressed through this formula. So let me represent by, let me take x in R. I will represent by dx. This is a measure in M, and dx of a set A will be equal to 1 if x belongs to A and 0 otherwise. So this measure, it's concentrated on the point x. The measure of a set will be either 1 if x belongs to A and 0 if x doesn't belong to A. So this measure, well, then I can represent, if I give you w, which is a positive number, I can have w dx, which is a new measure, which gives weight, instead of 1, omega if x belongs to A, and 0 if x doesn't belong to A. So what I'm saying here is that a measure mu is discrete if mu can be written as the sum over all j of pj dxj. Right? So if there exists a countable set D, and D therefore can be written as xj, this set X, I can enumerate the points of D, and weights pj, for which mu is given by that. So observe that if I take a set A and I want to compute mu of A, this is the sum of pj dxj of A, but dxj of A will be either 1 or 0, so mu of A, it's equal to gj pj dxj of A, and dxj of A will be either 1 or 0, so it will be 1 if xj belongs to A, and 0 if not, so I can rewrite this sum as the sum of over all j for which xj belongs to A times of pj, and this proves that indeed mu is given by this expression. So these are the discrete measures. And in the next blackboard, I will relate discrete measures to jump functions. So I'll define what a jump function is, and I will show that a measure is discrete if and only if the function associated to this measure is a jump function. So definition. So a function f in F is a jump function so the idea is that it's a jump function if it increases only by jumps. And how to translate that into a formal definition? Well, if there exists a countable set D, and here again I will write D, I will enumerate D, so D will be xj, j larger than 1, and sets of weights pj, such that fx will be equal, so I want fx, so I will sum pj over all j for which xj it's less or equal than x. Okay? And well, this is reasonable because if you remember that fx should represent m minus infinity x, if you want m to be the discrete measure associated to the countable set D and the weights pj, that should be equal by the previous definition to the sum for all j such that xj belongs to minus infinity x of pj. But this is exactly the sum over all j for which xj is less or equal than x of pj. So let me give you an example of a function f which is a pure jump. Well, let's take a function f which is equal to 0 up to some point x, and then at x it jumps and it takes some value p from x to the right of x. So let's say that at x it's equal to p, and on the left of x it's equal to 0. So this is of course a jump function, and the countable set D is just the point x, and the weight pj is just the weight p. So that's an example, that's a very simple example, but mind that a jump function can be much, much more complicated, because here D it's a countable set, so we can have a countable set which is dense. So D can be a countable, dense set of R. Take the rational numbers. So you take a Pj, a sequence of weights. What I didn't ask here, but I should, is that if you sum, so let me add to this definition the fact that for all x, so for this function f to be in f, I need fx to be finite, so I need this sum to be finite for all x, right? So I didn't stated that, but let me add this assumption to ensure that my function f belongs to f. So I want that for all x, that this sum is finite. Okay? Otherwise, fx would be infinite, and I would have a function outside of this set. So let me add this assumption, which I forgot. And in general, if you don't want, you can relax this assumption just by requiring that this sum for all y smaller than x, the sum of xj, so that will ensure that the measured sigma finite. Okay, but I'm requiring a bit more. I'm requiring fx to be finite, so I'm imposing that condition. So let me leave that condition. So let me take d. So I was mentioning the fact that jump functions can be quite complicated. Take a countable set, dense set of R, say the rationals. Take a family Pj, which write D, my countable dense set, as xj. Consider a set of weights Pj for which that condition holds. And now define fx by this formula. So you see the situation now, it's much more complicated, because if you take any point x, you have a dense set of jumps. So you have here jumps which are smaller and smaller as you approach x, but you have a sequence of dense jumps as you approach x on both sides. So, well, it's, if you think a bit, it's a bit difficult to figure out what is how this function really looks if your set is dense, or if you have an accumulation point of jumps at one point x. So, though the definition is quite simple, well, these functions are may be quite complicated to draw, for instance. So now let me state and prove the first lemma. The first lemma tells you that you have a one-to-one relation between mu, which is a discrete measure, and f of mu, which is a jump function. So what this lemma tells you is the following. Well, let's consider mu in M, and let's assume that this measure mu, it's a discrete measure. Define f mu, then I claim that f mu is a jump function. And the converse, take a function f, which is a jump function, consider the measure mu f in f, which is a jump function. Let's define the measure mu, which is associated to that function. I claim that mu is a discrete measure. The proof of this lemma is very simple. So let's assume first that mu in M is a discrete measure. If it's a discrete measure, there exists a countable set, D, and weights. So let's write D in this way, dxj. And there's also a countable family of weights, Pj. then once you're given that, you know that mu, since mu it's the discrete measure associated to this set and these weights, mu of A, it's equal to the sum for all j such that xj belongs to A of pj. Right? So by definition, f of mu of x, which is mu of minus infinity x, well, mu of minus infinity x by this formula is just the sum over all j such that xj it's smaller than x, right, of pj, and this shows that f mu is a jump function because, well, it fulfills the condition, and the fact that this sum it's finite follows from the fact that mu belongs to M, because we know that if mu belongs to M, this measure is finite, and therefore this sum is finite. So this proves that if you have mu a discrete measure, then the monotone function associated to mu, it's a jump function. Let's prove the converse. So now let's assume that f is a function in f, which is a jump function. Okay. So by definition, we know that there exists a countable set D, a family of weight pj, and we know that such that this expression holds, and we know that this expression is finite because f belongs to the set f. Fine, but then by definition, once you have this function, remember that I define mu of f of minus infinity x to be f of x, and f of x, by definition, is the sum. Okay, so mu f of this set is given by this formula. Let me introduce a measure nu on R with the Borel sigma algebra. And what is nu? Well, nu is the discrete measure associated to D and Pj. So nu of A is the sum for all j such that xj belongs to A of Pj. So we know that nu belongs to M, and this defines, this formula defines a measure on this measurable on the Borel sigma algebra. And now observe that nu and mu f coincide for these sets, because if I take nu of minus infinity x, by this formula, this is just the sum over all j, for which xj it's less or equal than x of pj. And this is exactly the formula we have for mu f. Okay? So we have this identity for all x, and this means that the measure nu and mu f coincide on the semi-algebra generated by the intervals a, b. Since these two measures coincide in the semi-algebra and the extension to the Borel sigma algebra is unique, these two measures coincide, and this proves that actually mu f is equal to nu, which means that mu f is the discrete measure associated to the countable set D and the weights pj, which proves that indeed mu f it's a discrete measure, and this proves the lemma. So my second lemma will say that if I take mu, a measure in M, then I can decompose mu as the sum of mu1 plus mu2, where mu1 it's discrete measure. And mu2, a measure with no atoms, which means that mu2 of x, it's equal to 0 for all x. And this decomposition is unique. So let's prove that. And again, the proof is very easy. So let's take mu in M. Let me define D as the set of x such that mu of x is strictly positive. So we've seen that D is countable. We proved that D is countable. If D is countable, let's enumerate D. So D will be equal to xj for j greater or equal to 1. And let's call Pj mu of xj, mu of the point xj, which is strictly positive. Now let me define mu1, as the measure, the discrete measure associated to D and to Pj. So mu of A, it's equal to the sum for all j such that xj is in A of Pj. But remember, this is the sum in j such that xj belongs to A of mu of xj, and therefore this is mu of D intersection A, right? Because D I can enumerate as the xj, so I can take the sum, and there I get xj intersection A, so that will be 0, the empty set, and therefore mu of 0 if xj doesn't belong to A, and it will be mu of xj if xj belongs to A, so I get this identity. And therefore this measure is smaller than mu of A. So I get that this measure mu1, which is a discrete measure, it's smaller or equal than mu. Therefore I can define mu2 as mu minus mu1, so this is a non-negative measure, right? And if I take mu2 of a point x, well, this is mu of x minus mu1 of x. If x doesn't belong to D, mu of x is 0, and mu1 of x, it's also equal to 0, right? Because if I take x outside D, well, that sum will be an empty sum. On the other hand, if x belongs to D, mu of x, it's equal to x will be 1 of the xj, mu of x will be pj, and mu1 of x will also be pj, so that difference is 0. So this shows that mu2 of x is equal to 0 for any x, which proves that mu has no atoms. Therefore, we have obtained the decomposition we were looking for, because mu it's equal to mu2 plus mu1. Mu1 it's a discrete measure, and mu2 has no atoms. So that proves that this decomposition is possible. Now let's show that it's unique. So to prove uniqueness, let's write mu1 plus mu2 equal to mu1 plus mu2. So this one, I'm assuming these mu1 and mu2 are discrete. While mu2 has no atoms, and mu2 has no atoms. Okay. Well, since this measure is discrete, it's associated to a countable set D1 with weights P1. And this one, it's also associated to a countable set D2 with weights P2. Now, take a point x in D1. Mu, so x in D1, x will be equal to some xj. The measure of x with respect to mu1 will be some p1j. Mu2 of x, it's equal to 0. So by this, and mu2 of x will be equal to 0. So I have that mu1 of x, it's equal to nu1 of x. This shows that d1 has to be equal to d2 and p1 has to be equal to d2. So maybe it's not clear, but let me take a point x. Let me take the measure of that point. From this identity and from the fact that mu2 and nu2 have no atoms, what we get is that mu1 of x, it's equal to nu1 of x. Okay, and this holds for any x in R. And since from that inequality we have that the countable set D1 has to be equal to the countable set D2, and the weights have to be equal to. Which proves that mu1 is equal to nu1, and if mu1 is equal to nu1, we get that mu2 is equal to nu2, and this proves the lemma. So this proves the uniqueness of the decomposition. Now we have a simple remark. We have seen in this decomposition that measures with no atoms appear. So suppose that mu has no atoms. And what I claim is that this happens if and only if f mu is continuous. Okay, so this remark or this lemma is stating that, well, take a measure mu in M. If it has no atom, then the associated function, monotone function, is continuous. And the converse states that, well, if you take a function f in F, which is continuous, then the associated measure has no atoms. And the proof of these lemma, it's very simple, of this remark is very simple. Take mu with no atoms. We have seen that f mu of x minus f mu of x minus, so the left limit at x, this difference was exactly equal to mu of x. Well, but since mu has no atoms, this is 0. This means that the left limit is equal to the right limit, and since f is monotone, this means that f is continuous. So this proves this direction. And for the other direction, well, suppose that f is continuous. Define mu of f. Well, you have this relation, f of x minus f of x minus, it's equal to mu f of x. Since f is continuous, the left limit coincides with the right limit. Therefore, this is 0, which means that this expression is 0. If this is true for any x, this means that mu f has no atoms, and this is the claim. So we have this remark. We have proved this remark. So measures with no atoms are associated to continuous monotone functions, and therefore, if I have a function f, which is monotone and belongs to my set f, I can associate to that function a measure mu f, which is in my set M. By this lemma, I can rewrite mu f as mu f1 plus mu f2, where that function is discrete. It's a discrete, it's a discrete measure, and this measure has no atoms. This means that, let me represent by f1 the monotone function associated to that measure, and by f2 the monotone function associated to that measure. Since this measure is discrete, this means that this is a jump function. And since this measure has no atoms, this means that this function is continuous. Okay? Now, it's clear that if you take a measure mu and you decompose it as a measure mu1 plus mu2, and you define by f of mu the function associated to mu, and by f1 the function associated to mu1, and by f2 the function associated to f2, what I claim is that f of mu is equal to f1 plus f2, and this is obvious because f mu of x it's equal to mu of minus infinity x, which is equal to, by this formula, mu1 of this set plus mu2 of the same set. But mu1 of this set is f1 of x, and mu2 of this set it's f2 of x. And therefore, f of x it's equal to f1 plus f2. So the measure, the monotone function associated to mu f, it's f. And therefore, we proved that f can be written as the sum of a jump function and a continuous function, right? Because so this lemma, translated to functions, tell us that any monotone function can be written as the sum of a pure jump function and a continuous function. So now we have a continuous function, and we want to say that this continuous function now can be written as the sum of an absolutely continuous function and a singular function. So this is the next step of this lecture. So I proved that if I have a monotone function f, I can write it as the sum of a jump function plus a continuous function. So this is a jump function, and this is a continuous function. So now I'll concentrate on continuous functions. So from now on, I will assume that f is continuous. My lemma, my next lemma, say this is, I guess, Lemma 3, is that, well, if mu in M is absolutely continuous with respect to Lebesgue, this happens if and only if f of mu is absolutely continuous. And again, this means that if I have a measure mu which is absolutely continuous, then the associated monotone function is absolutely continuous. And conversely, if f in f is absolutely continuous, then the measure associated to it is absolutely continuous with respect to the Lebesgue measure. So let's prove that. So let's assume that mu is absolutely continuous with respect to the Lebesgue measure. Well, if mu is absolutely continuous with respect to Lebesgue measure, we know that mu, there exists a function a, f, such that mu of a is equal to the integral of f d lambda, right? And if I specialize that to intervals, say ab, or let's first take minus infinity x, well, this is the integral from minus infinity x of f d lambda. And by definition of f, this is also f mu of x. So we proved that f mu of x is given by this expression. And if you're concerned with the minus infinity, you can just then say that f mu of y minus f mu of x, it's equal to the integral from x to y of f d lambda. And we have seen that if a function f is can be written as the integral of well, this function f, mind it's integrable over all finite intervals. So this is an integrable function in any interval minus n. And we have seen that if a function f satisfies this identity, then it is absolutely continuous. Okay. So this proves that f of mu is absolutely continuous, a function, and proves one direction of the lemma. So now let's prove the other direction. So let me take a function f in f, and let's assume that f is absolutely continuous. If f is absolutely continuous, this means that fx minus, say, f0 will be given by the integral from 0 to x of f prime d lambda. And this is mu. So, more general, fy minus fx will be given by the integral from x to y of f prime d lambda. And this is mu f of the integral xy. So mu f of the integral xy is given by this formula. So now let me define and measure nu on the Borel sets of the line, and I will define nu of a as the integral over a of f prime d lambda. So this measure nu, it's absolutely continuous with respect to the Lebesgue measure, right? Because this function f prime, it's integrable over finite intervals. So if I take a set A which has Lebesgue measure 0, this integral is equal to 0, and this shows that nu is absolutely continuous with respect to Lebesgue. So nu, it's absolutely continuous with respect to Lebesgue, and nu and mu f coincide in the intervals xy. This shows that they coincide in the semi-algebra, and since the extension to the Borel sigma algebra is unique, this proves that nu is equal to mu f, and therefore, since nu is absolutely continuous with respect to lambda, mu f it's also absolutely continuous with respect to lambda, and this proves the converse assertion. So this proves Lemma Three, and therefore we have a characterization between absolutely continuous functions and absolutely continuous measures. So let me recall the definition of a singular function. F in f is a singular if f is continuous and f prime it's equal to 0 almost everywhere. Okay. And the lemma which I want to prove now says the following. Well, mu is non-atomic and singular if and only if f of mu is singular. And here I mean singular with respect to the Lebesgue measure. So remember that we have a measure mu. Mu can be written as always one piece which is absolutely continuous with respect to the Lebesgue, and the other piece which is singular, and that singular means that there exists a set A such that mu of A it's equal to 0 and lambda of A complement it's equal to 0. So this is what I mean here by singularity of this measure mu with respect to the Lebesgue measure, so that I can find A in B such that mu of A is equal to 0 and lambda of A complement is equal to 0. So this lemma states the following. Take a measure mu in M, assume that it's non-atomic and that it's singular with respect to lambda. Then I claim that the associated monotone function f of mu is singular, where the definition of singularity is here for functions, which means that f of mu is continuous and its derivative is equal to 0 almost everywhere. And the converse means the following. Take f, a function f in f, which is singular. Take mu, the measure which is associated to that monotone function. I claim that mu is non-atomic and singular. So let's prove this lemma. So let's assume first that mu is non-atomic. And singular. Okay, we've seen that if mu is non-atomic, so let me represent by f of mu the monotone function associated to mu. We've seen that if mu is non-atomic, then f of mu is continuous. That we already proved. Okay, so the first property holds. Now let's prove that f prime of mu is equal to 0. For that, let me define nu of, this is a measure, nu of A, which is given by the integral of over A of f prime d mu. Okay? We know that f prime is non-negative and it's integrable over finite intervals, because we know that the integral over ab of f prime, that this is bounded by f of b minus f of a, right? So f prime is integrable, so this measure is well defined. Okay. Now I know that mu is singular with respect to mu, to Lebesgue. This means that there exists a set, here I called A over there A, so maybe let me not use the same set. So this is B, and this is B, and this holds for all B in B. Okay, so this is the definition of my measure nu. And since mu is singular, I know that there exists a set A such that mu of A it's 0, and lambda of A complement is 0. Okay, so now remember that nu of B is given by this expression, and as I wrote, A f d lambda, that this is less or equal than f b minus f a. Okay, and this, by definition, it's nu of ab, right, by definition, while this expression here, by definition of mu, it's mu f ab. So we have that this inequality holds for these sets, and we can, by using monotone class theorem, shows that in fact mu is less or equal than mu f. Okay. So, well, we have this inequality, then we extend this inequality to the algebra, and then by the monotone class theorem, we extend this inequality to all elements of the sigma algebra. So what I'm writing here is that for all elements of the sigma algebra, nu of b it's less or equal than mu f of b. So we have this inequality. And what I claim is actually that nu it's equal to 0. Okay? And why is that so? Well, because write nu b as nu b intersection A plus mu B intersection A complement, where A is this set. Okay. Well, on the one hand, we know that mu of A is equal to 0. Okay. So mu of B intersection A, it's less or equal than, well, this is actually my measure mu, right? Because f, it's f of mu. So this is mu of AB. So we know that mu, it's less or equal than mu. So the measure of this set, it's less or equal than the measure of B intersection A with respect to mu by that inequality. Okay. And B intersection A, it's contained in A. So the measure of that set, it's smaller than the measure of A, and the measure of A is 0. So this set here, it's equal to 0. On the other hand, mu of B intersection A complement, it's equal, and here I wrote mu, but it's respect to Lebesgue, of course. So nu of B by this definition, it's the integral over the set B intersection A complement of f prime d lambda. Well, A complement has Lebesgue measure 0, and therefore this integral, since f prime it's integrable over a finite set, this integral it's equal to 0. Okay. So this proves that the measure of the second set it's also 0, which proves that for any set B, nu B of it's equal to 0, which is what I claimed, that nu it's equal to 0. Well, if nu B it's equal to 0, f prime, which is given by in this formula, has to be equal to 0 almost everywhere, right? Because if f prime was not equal to 0 everywhere, we could find a set B for which this integral was strictly positive, and therefore we'll find a set B for which nu of B is strictly positive, which we just proved it's not possible. Okay, so this proves that nu is identically equal to 0, and from that we conclude from this formula that f prime has to be equal to 0 almost everywhere. So this proves that if mu it's non-atomic and singular with respect to the Lebesgue measure, then f mu is singular. And now we will prove the converse. So let me erase the proof, and let's prove the converse. Right. So now I want to take a function f in f, which is singular, and I want to prove that the associate measure mu f is non-atomic and singular with respect to the Lebesgue measure. Right? Well, so let's assume that f it's singular. F it's singular means that f it's continuous and f prime it's equal to 0. Since f is continuous, we've seen that the associated measure it's non-atomic. So we already know that it's non-atomic, and now we need to prove that it is singular with respect to the Lebesgue measure. So mu of f mu f it's equal to fb minus fa. I know that mu can be decomposed. So let me take f prime, the derivative of f prime so we know that mu can be decomposed as mu1 plus mu2, where mu1 it's absolutely continuous with respect to Lebesgue, and mu2 it's singular with respect to Lebesgue. So in order to prove that mu f it's singular with respect to Lebesgue, we have to show that mu1 is actually equal to 0. So that the absolutely continuous part with respect to Lebesgue it's equal to 0, and therefore mu it's equal to mu2, which is only the singular part. Well, but mu1 it's absolutely continuous, which means that mu1 of A, or A is not a good name for the set, mu B, mu1b, can be written as the integral over B of G d lambda. Right? We know that if mu1 it's absolutely continuous with respect to Lebesgue, there exists the Radon-Nikodym derivative, which I'm representing here by G. So the measure mu1 of any set B can be represented by this expression, which means that mu1 of AB, right, it's mu1 of AB, which is the integral over A to B of G d lambda, that this set, this measure, due to that inequality, because since mu f it's mu1 plus mu2, mu1 AB, it's less or equal than mu f AB, and mu f AB, I wrote it here already, this is bounded by fb minus fa. This is equal, I'm sorry, to fb minus fa. So this shows that this integral, it's bounded by fb minus fa for all a and b, right? So maybe let me repeat. I'm assuming that f is singular. I'm taking the measure associated to the function f, I'm calling mu f. This is the notation. And I'm using the Radon-Nikodym theorem to say that mu f can be decomposed as a piece which is absolutely continuous and a piece which is singular. And if I want to prove that mu f is singular, what I need to show is that mu1 is equal to 0, so that the absolutely continuous part is equal to 0. Fine. Since mu1 is the absolutely continuous part, we know that for any set B, mu1b can be written as the integral over B of some function g d lambda, where g is the Radon-Nikodym derivative of mu1 with respect to lambda. Okay. So in particular, if I take the interval ab, mu1 of ab is the integral over ab of g d lambda. And this, since mu1 plus mu2, which is non-negative, it's equal to mu f, mu1 of ab, it's bounded by mu f ab. So mu1 ab, which is equal to that expression, it's bounded by mu f ab, and mu f ab, we know it's fb minus fa. So we have that this integral is bounded by that one. So a, b, g d lambda, it's less or equal than fb minus fa. And this holds for all ab. A less or equal than ab. Okay? So let me call this function the function g b minus ga. Okay? So let me call g the integral over this small g. And what we know is that g prime of x, so it's almost surely equal to g of x. So this is almost surely equal to g of x. And on the other hand, by that inequality, if you divide it by b minus a and you let b to converge to a, what you get from this inequality is that g prime is less or equal than f prime. Right? It follows from this inequality, if you divide that both sides by b minus a and you let b to decrease to a, is that, well, if it exists, g prime of a, it's bounded by f prime of a. So g prime is less or equal than f prime almost everywhere, but g prime is equal to g, so I know that g it's less or equal than f prime almost everywhere, right? But by assumption, f prime is equal to 0. So that proves that g is equal to 0 almost everywhere because g is non-negative. G is the Radon-Nikodym derivative. So that proves that g is equal to 0 almost everywhere, and therefore that mu1 of the interval AB is equal to 0. Therefore, mu1 is equal to 0, and this proves that mu f is actually equal to mu2, which is the singular part with respect to lambda. So that proves that mu f is singular with respect to the Lebesgue measures, and that proves the lemma. So now we are almost done. Let's take a function f, which belongs to f and which is continuous. Then I claim that f can be written as f1 plus f2, where f1 is absolutely continuous and f2 it's singular. Well, that's easy because we have all elements to prove that. Take a function f in f which is continuous. Let mu f to be the associated measure. We know that this measure has no atoms. And by the Radon-Nikodym theorem, we know that mu f can be written as mu1 plus mu2, where mu1 is absolutely continuous with respect to Lebesgue. So let me write that this way. And mu2, it's singular with respect to Lebesgue. So let me represent by f1 the function associated to mu1, and by f2 the function associated to mu2. We know that the function f associated to mu f, which is f, we've seen that if f1 is associated to mu1, f2 to mu2, and we have this identity, then we have that identity. Mu1 is absolutely continuous, and we have seen, therefore, that f1, we've seen in the previous lemma that f1 is absolutely continuous. Now we know that mu2 is singular with respect to Lebesgue and has no atoms. This proves that f2 is singular, and this proves the lemma. So f1 is absolutely continuous and f2 is singular. So now let me state the theorem we proved, so that if we have a function f in f, then f can be written as f1 plus f2 plus f3. f1, it's a jump function. f2, it's an absolutely continuous function. And finally, f3 is a singular function. right? Because we proved that f can be written as f1 plus f2, where f1 it's a jump function, and f2 it's a continuous. And then we proved that if we have a continuous function, the previous lemma said that if f2 is a continuous function, it can be written as f3 plus f4, where f3 it's absolutely continuous and f4 it's singular. So this proves the theorem which I stated at the beginning of this lecture,